Okay, so our next talk is stateful dynamic partial order reduction for model checking event-driven applications that do not terminate. And it will be given by Weiyu. Go ahead.
Hi, my name is Weiyu. Today, I'm going to present a paper, Stateful Dynamic Partial Order Reduction for Model Checking Event-Driven Applications that do not terminate. This is a joint work with Rahmadi Trimananda, Brian Demsky from UC Irvine, and Harry Xu from UCLA. Event-driven systems are prone to concurrency bugs. Subtle execution order of different events can lead to unexpected failures of event-driven apps. Model checking tools are very helpful to detect bugs in such systems. Our work is inspired by smart home IoT apps, and we will use them as a motivating example. When multiple apps can control the same device, some conflicts may occur. Suppose that we have Smart App 1, Fire CO2 Alarm. What the app does is to sound alarm and unlocks the front door when the sensor detects smoke. Suppose we have a second app, Lock It When I Leave. What the app does is to lock the front door when the sensor detects someone leaving the house. If a homeowner installs both apps, then the two apps can have some conflict over whether to lock or unlock the door. Let's imagine one day, there's a fire, and there are 5 people in the house. The Fire CO2 Alarm app sounds alarm and unlocks the front door because it detects heavy smoke. Then when the first person leaves the house, the Lock It When I Leave app locks the front door. So the question is whether the door should be locked or unlocked. This is some conflict that may occur. This is an example event-driven system. We have an event queue where the events can come from different sources, such as cloud services, mobile devices, and other devices. When events are dispatched from the event queue, an event handler is executed and change the state of devices. To simplify the concurrency model, we make the following assumptions. First of all, the system has a finite set of event types, where each event type has a corresponding event handler. Second, the event continuously dispatches events. This is assumed to be non-terminating, because smart home apps are intended to run without termination. Third, an event handler may contain several accesses to the shared state of the system. Lastly, an event handler is executed atomically without preemption. Although our work is inspired by smart home IoT apps, our algorithms and techniques are general enough to apply to other event-driven systems if they satisfy the assumptions in our paper. The state-of-the-art model checking tools fall into two categories. The first category is stateless model checking, such as R4 by Jensen et al. R4 is in the domain of event-driven applications. It uses the technique of partial order reduction to model check web applications. Although there are many other stateless model checking tools in the recent years, most of them are in the domain of multi-threaded programming. For stateful model checking, we are not aware of any recent work in the domain of event-driven systems. Both the work by E et al. And the Inspect tool are in the domain of multi-threaded programming. There are both stateful model checkers that combine with dynamic partial order reduction. However, as far as we know, none of the DPOR algorithms mentioned above can handle programs with cyclic state spaces. Therefore, simply adopting their algorithms in the domain of event-driven applications will not work. For stateless model checkers such as R4, the users need to bound the execution length in order to verify programs with cyclic state spaces. However, doing so can only be considered as an approximation. The Inspect tool is designed to verify programs that terminate, so it cannot handle programs with cyclic state spaces. The work by E et al. Claims to handle programs with cyclic state spaces, However, we will show an example shortly where their algorithm fails to find a bug. Our work solves this problem by designing a stateful DPOR algorithm that can handle event-driven systems with cyclic state spaces. The outline of this presentation is as follows. I've just gone over the background and the motivation for this work. The second part, I will talk about the challenges that we've encountered and the techniques that we've developed. The third part is our new algorithm. And the last part is the implementation and the evaluation. Next, I will talk about the challenges that arise when applying existing DPOR algorithms to check programs with cyclic state spaces. The first challenge is the premature termination of stateful algorithms when they are applied to programs with cyclic state spaces. This problem is well known in partial order reduction literature, and different provisos or conditions have been proposed to solve the problem. Although this problem is well studied before, existing stateful DPOR algorithms still produce incorrect results on programs with cyclic state spaces. We will show an example. In this multi-threaded example, there are three variables x, y, and z, and we have three threads, T1, T2, and T3. T1 increments x, T2 has a while loop, and it keeps reading from the variable y. T3 reads from z, increments x, and checks if R4 is 0. Let's suppose that in the first execution, the algorithm selects T1 to take a step, increments x, and we reach the state S1. Now the algorithm selects T2. After the first iteration of the while loop, it revisits the same state. At this point, the stateful DPOR algorithm will stop because it revisits the same state. And the algorithm terminates here because we didn't set anything in the backcheck set. So we miss the execution B where T1 takes a step and T3 takes a step and eventually have an assertion failure. Both the inspect tool and the work by E et al. Will miss the execution B. The inspect tool doesn't support programs with cyclic state spaces. An algorithm by E et al. It overlooks the need for a condition for when it's safe to stop the current execution. So it also stops after the execution A. To deal with the issue, we came up with our own new termination criteria. Our algorithm will terminate the current execution and explore other actions in the backtrack set if one of two conditions is met. The first condition is we have a state match. A state match is when we revisit a state that has been explored. So the first condition is when we have a state match from previous execution. Or the second condition is when we have a state match from the current execution. And in the cycle between two visits to the same state, all the enable events are explored in the cycle. To illustrate the second condition, suppose we have an execution where the algorithm explores from state S1, S0 to S1, S2, and all the way to S5, and then back to state S2. Since S2 is visited twice, there's a cycle. If in the cycle it contains all the events that are enabled at the states in the cycle, then the second condition is met. Going back to the previous example, with the new termination condition, at state S1, after we have the first iteration of the while loop and going back to the same state, the algorithm will not stop because in the cycle, it doesn't contain all the enabled transitions. And there will be a chance to execute the second execution, the execution B. Although this example is multi-threaded and we phrase our termination condition in terms of event-driven systems, the idea should be similar. The second challenge is the difference between traditional DPOR in multi-threaded programming and DPOR in event-driven systems. In traditional DPOR, A transition is a single access, so the effect of a transition can be determined without executing it. However, in event-driven systems, the effect of an event handler cannot be determined without executing it. As previous work by Jensen et al. Has noted, an event handler may contain several or even a large number of instructions, so we cannot determine the effect without executing it. A naive approach is to execute the event handler and then roll back, but this approach is not practical because it's likely to incur a large overhead. Also, an event handler can access multiple memory locations. Traditional DPOR only sets a backtracking point at the last conflicting transition. We will show an example to show the problem of this approach when it's applied to event-driven systems. In this example, there are two variables, x and y, initialized to 0, and we have three events, E1, E2, and E3. E1 writes to y, E2 writes to x, and E3 says if x equals 1, then observe that y is also 1. Let's suppose in the first execution, the algorithm executes E1, E2, and E3. There's a conflict between E2 and E3 because one writes to x and one reads from x. If we only set backtracking points at the last conflicting transition, then E3 will be added to the backtrack set of state S1. And in the next execution, we will execute E3 from the state S1, and it will revisit the same state. Since we've explored all the events in the backtrack set, the algorithm will stop. And we miss the execution where E2 takes a step, followed by E3, and then we have the assertion failure. Our technique is to compute basis on a per memory location basis and set backtracking points for each conflicting memory location. So going back to the example, other than the conflicts between E2 and E3 in the first execution, there is also the conflict between E1 and E3 because both one reads from Y and one writes to Y. Since we have an earlier conflict with event E2 and E3, so event E2 should be added to the backtrack set of state S0. And then the algorithm is able to execute this execution. Oh, sorry, I forgot to mention that in this example, we assume each event can only be executed once. The next challenge is how to update backtrack set on the state match. Some previous work on stateful DPOR has noted that simply terminating the current execution on the state match is unsound. They use a graph to store explored transitions and states in order to set backtracking points in the current execution, without to re-execute the same transitions once again. An idea is borrowed from stateless model checking, stateless DPOR. For example, if we have two transition sequences, S and S prime, that both reach the same state, Si, and S prime is a later transition sequence that reached the state Si. Then from Si, they will explore the same transitions and states. So stateless DPOR will set backtracking points in both S and S prime. When the same thing happens in stateful DPOR, if we have a graph that stores the visited states and transitions, then in the transition sequence S prime, we can use the graph to set backtrack points in S prime without re-exploring the same states and transitions. In our algorithm, we use a state transition graph similar to graphs used by previous work to store explored transitions and states. A state transition graph is a directed graph where nodes are visited states and edges are explored transitions. In the paper, we make a difference between a transition and an event. An event handler executes a sequence of instructions. However, the same event handler can have different effects when it's executed at different states. So a transition is the effect of an event handler being executed at a state. The technique of state transition graph works well for programs with acyclic state spaces. However, when we use it together with our new termination condition to model check programs with cyclic state spaces, some new problems appear. The issue is that the previous visited state may not have been completely explored. And this is an example. We have three variables, x, y, and z, and four events, E1, E2, E3, and E4. E1 writes to x and z, E2 reads from z and writes to y, E3 writes to y, and E4 has an insertion failure if x equals 0 and y equals 1. Let's suppose in the first execution, the algorithm executes events E1, E2, E3, and E4. There's conflict between E1 and E2, so E2 is added to the backtrack set of S0. There's a conflict between event E2 and E3 because both write to variable y, and E3 is added to the backtrack set of state S1. There's also conflict between state E1 and E4, both events write to x, so E4 is added to the backtrack set of state S0. Since executing event E3 and E4 both have state matches, so the users of state transition graphs will add E1 to the backtrack set of S1 and E2 to the backtrack set of S2. Next, the algorithm will explore the backtrack set of state S1. It will execute event E3 and E1 from the state S1. They are shown in the executions B and C. And executing E3 and E1 from the state S1 will both revisit the same state. Since the state S1 is explored in previous execution, executions B and C will stop. In the next execution, it will execute event E2 from the state S2, and again, it revisits the same state. We still have events E2 and E4 in the backtrack set of state S0. Suppose that in the next execution, we execute E2 from state S0 and we reach a new state S3. Since it's a new state, the algorithm will randomly pick an enable event. Let's say it picks event E3 and then revisits the state S0. E2 and E3 have a conflict because both write to y. So E3 is added to the backtrack set of state S0. And since we have state match after executing E3, the state transition graph will, the algorithm will add E2 to the backtrack set of state S3. Next, the algorithm executes E2 from the state S3 and revisits the same state. In the end, we execute E4 and E3 from the state of S0. They are shown in the executions G and H. However, the assertion failure in E4 is not triggered, and we miss the execution where E2 takes a step from state S0, and then E4 takes a step and have the assertion failure. We found the issue is the following. If we have explored the transitions on the right, a loop, in some previous execution, and then explore the transitions Tj and Tk in the later execution, the algorithm should not only set backtracking points in the execution on the left, but also set backtracking points in the loop explored in previous execution. So to address the issue, we've designed a new algorithm that performs backward depth-first search on the state transition graph to set backtracking points on previously discovered path or previous executions. Next, I will talk about the algorithm. Our algorithm is a combination of the techniques that I've talked about before in the last part. So first, we have our new termination criteria. And second, we compute conflicts on a per memory location basis and set backtracking points for each conflicting memory location. Third, we have a state transition graph to store explored transitions and states, and we use a backward DFS algorithm to set backtracking points on previously discovered path. We give a proof of our algorithm in the extended version of the paper that is published with the same title in the archive.org. In the proof, we first show that our algorithm terminates on the state transition system with finite reachable state, where the system can be cyclic. And then the algorithm explores the necessary states in order to verify local assertions or safety properties when it terminates. Next, I will show a running example of our algorithm on the last example. Since the last example is already very similar to how our algorithm works, except that now we add one last piece that will add backtracking points in previously discovered path. So I will skip the first few executions that are the same. The difference is at the execution age. In the execution age, we execute event E4 from the state of S0. Let's take a closer look at the executions E and H. There's a conflict between the event E3 and E4, both access the variable Y. So the backward DFS algorithm works. It's as if the event E4 is executed on top of the execution E. So it will find the conflict between E4 and E3, and then add E4 to the backtrack set of state S3. Now executing event E4 from the state S3 will give us the assertion failure in the execution I. Next, I will talk about the implementation and evaluation. We implement our algorithm by extending the IoTCheck. IoTCheck is a stateful model checker that verifies some smart things, smart home apps. IoTCheck itself does not implement dynamic partial order reduction. We did not compare our tool with other tools on event-driven systems, such as R4 or the work by Maya et al., because their tools cannot handle programs with cyclic state spaces, and the tools were implemented in different domains, such as web applications or Android applications. So it's not straightforward to adapt their tools to run on smart home apps. Our dataset is taken from the dataset of IoTCheck smart home apps. The original benchmark that we selected contains 1,400 pairs of apps. We excluded some apps that finish with their execution within 10 seconds because they usually generate a very small number of states. And we also excluded apps that are too similar. And finally, we have a dataset of 535 pairs of apps. In our experiment, we run each pair of apps for 2 hours with 32 gigabytes of memory under two modes, the DPOR mode and the without DPOR mode. Among the 535 pairs of apps, only 300 pairs finish in 2 hours under at least one mode. The other apps either run out of memory or out of time. Among the 300 pairs of apps, 229 pairs finish under both modes, and 69 pairs finish under the DPOR mode. There are 2 pairs that finish without DPOR, but were unfinished with DPOR. After some investigation, we found that the 2 pairs are very challenging for our DPOR algorithm because they generate a large number of read-write and write-write conflicts. This table shows 10 pairs of apps with the most number of states. All of them finish under both modes. These apps also generated a large number of read-write and write-write conflicts when model checked with our DPOR algorithm, so our algorithm did not significantly reduce the number of states, transitions, and the runtime. Overall, our algorithm achieves a 2 times state reduction and a 3 times state transition reduction for the 229 pairs that finish under both modes. If we count the runtime of the unfinished apps as running for 2 hours, then we achieve an overall 7 times speedup for the 300 pairs using the geometric mean. In conclusion, our technique combines stateful model checking with dynamic partial order reduction, and it's the first algorithm that can handle event-driven applications with cyclic state spaces. Thank you very much for your attention. Our software and dataset is available in the GitHub.
Thank you.
Thank you.
Okay, let's see if there's any questions from the in-person audience or in Q&A.
Yeah, we have one question. 1 second.
Thank you, and Underka. I saw that you selected 225 pairs of apps, but in the results there were just 300. Did I miss something, or?
Oh, okay. I think I stopped sharing. Let me go back to the share. Can you see my screen now?
Not yet.
Not yet.
Yep,
Now?
it's working. Yep.
Okay, so we selected 535 pairs of apps, and we run the apps for 2 hours with the 32 gigabytes of memory. But only 300 apps, so these 300 apps, they finish under at least one mode. And the other 225 apps, they didn't finish under both modes, so it did not show them in the table.
Oh, I see. Thank you.
Thank you.
Okay, there's a question and Q&A from Andrew Johnson. And the question says, it's on the screen right now. Can conflicts be ignored if their effects do not interfere or can be shown equivalent?
I'm not very sure what the question means. So what do you
maybe
mean
Andrew
by
can clarify. So it says, for example, what if you have two events which both write to y, but they both write the same number to y? Do you still have to consider different orders of them?
Yeah, I think different orders are still considered. However, if we have two events that rise to y equals 2, then they will reach the same state, and one of them will be ignored by the stateful part, the stateful component of our algorithm. But if you have x equals 1 and then x equals 2, I think they cannot be ignored.
Okay, thank you. Do we have any more questions?
Not from the live audience right now.
So I have one short question. So you mentioned that you didn't compare with existing techniques because they cannot support cyclic state spaces. How does your technique work on acyclic state spaces? Like, can I use it to completely replace all other algorithms, or are they still better if I know there are no cycles?
Our technique still works for programs with acyclic spaces. So then the way it works, I mean, it's similar to stateless DPOR with stateful model checking.
I see. So you're saying that it is just, like you didn't compare it in that case because it would be the same technique?
I think the reason is like some of our benchmarks, they have cyclic state spaces. I mean, in the IoT apps, they are intended to run without termination. And so these apps are, I mean, all the IoT apps, they are considered to have cyclic state spaces. So we cannot run the other two tools on the IoT apps.
Okay, well, thank you. Let's thank our speaker.